Welcome to Chapter 6, Equilibrium, and we're going to be following along with the 9th edition Harris Quant Chemical Analysis textbook. Right, so let's get started. We're going to be talking about the idea behind equilibrium. So in an equilibrium, there is a chemical reaction that is happening, and at this state, which is known as equilibrium, the forward reaction, which is indicated by Kf in here, and your reverse reaction indicated by Kr, their reaction rate, as shown on this graph, is going to be equal. And at the same time, in this state, the concentration is also going to be the same. It's going to be constant. While also it's dynamic, meaning it's moving and it's not gone, or it's not ceasing. Okay. So just remember, the rates become equal. Your forward and your reverse reaction rates become equal when it's at equilibrium, and then the concentration becomes constant. So just remember also that the amount of each reactant and product becomes constant in equilibrium. Okay. So equilibrium constant. You need to learn some assumption in here. So one of the assumption is that the ratio of the rate constant, so what they meant in here is your forward and reverse reactions, your T in here is going to be constant, your temperature is going to be constant. So in this example, your N2O4 and O2, what they do is they write first KEQ, which is your equilibrium constant, is equals to your rate of your forward and then your rate of your reverse. And then since it's a concentration, it's going to be written as this way. NO2, and then the coefficient, which is a number, it becomes a power. So it turns above into 2. And then the N2O4, technically you have 1 there. It's going to be raised into a power of 1. Okay? So just remember, if we're going to generalize this reaction, we can write it this way. Okay? So this is your forward. This is your reverse. And in there, whatever atom you have, it's going to go here inside of the bracket, and whatever number turns into a power. So for example, in this one, your C, which is your atom, is put inside of the bracket, and then your small c turns into a power. And then you're doing the same thing with a big D, and your little d, which is your coefficient, turns into a power. Okay, so we're so good. Let's just review, and then we're going to do just C for this one. So for C, Ag plus NH3AQ, AgNH32AQ. So write first KQ equals Kf for Kr. So we're just following exactly what's happening here. Okay, Kf, all I see is the AgNH32 plus, and since there's none here, I'll just put a 1. Okay, whenever there's none in here, I'll just put a 1 as a habit, just so you won't forget the same procedure with the numbers. Okay, do the same thing. Ag plus, put a 1 there. Remember, there's 1 beside there, and then NH3, the number before that turns into a power. So that's it. Manipulating the K. So when it's a reverse reaction, it's going to be 1 over K. When you're multiplying a number, it's going to be K over N. And K, when added, is going to be multiplication. So if it's reverse, it's going to be reciprocal. If it's going to be multiplied, it's going to be turned into a power. And then this one is just going to be multiplied. So addition in here is multiplication. Multiplied by a number turns into a power. And when it's a reverse reaction, it turns into its reciprocal. Okay, so let's do it this way. Calculate the value of Kc for the reaction below. Okay, so N2O. N2O, as we can see, it's right here at the forward, but in this overall reaction, it turns into this stuff, right? It turns into forward. So we need to reverse this. Now, which one are we also going to reverse? How about our oxygen? Our oxygen is fine. It's where it's supposed to be, okay? How about our N2O4? Now the N2O4 is at forwards. We need to turn into its backwards position, okay? All right, so what else are we doing here? So also in here, I'm going to use a purple in here. So also my O2, it's going to be multiplied by 3. So far I have just so far I don't have that yet, okay? But we're gonna see how we can do that. And then we have 2 N2O4, so we're just gonna multiply 2, and this one turns into a 4, okay? All right, so and then our oxygen, right, from our example, okay, now I know this one's missing 2. Probably it's implied, but for this one, your oxygen, it's also going to be 2 in here, okay? And it makes sense, right? It also becomes 3. So we have 2 things that you need to reverse. So what I'll do it one by one. Red. So the red, which is the reverse, I'm just gonna do its reciprocal. So 1.2 times 10, 35. Then we're gonna add with 4.0 times 10 to the negative 3. Okay, so after you do that, right? Well, technically, after you do that, then you times it by 2, because it's a power. And then the bottom, you're just going to multiply that. So you're also turning that into a power. Since you multiplied it. Oh, sorry. Yeah, so it's going to be like that. Since we're not really adding, we're multiplying everything. This is your this is how your process is going to be. 1 divided by 2 times 10 to the negative 35 plus 1 divided by 4.0 times 10 to the negative 3 squared plus 6.0 times 10 to the negative 9 squared. And let me explain to you why again. So for your equation right here, we reverse this because we want the N2O to be right here on your the reverse reaction in this case. That's the reason why we did its reciprocal. In here, we reverse it. The reason why we reverse it is because we want the N2O4 to go here in the forward, okay? And we use this first rule, okay? So that's the reason why we have 1 times 10 to the 4.0 times 10 to the negative 3. And the reason why we squared it, which is the power, is because we want the N2O4 to be 2, And the only way we can make it 2 is to multiply everything by 2, which in this case, if you want to multiply something, you want to turn into power. And lastly, right here on the last one, we want to turn it into 2. And the reason why is because we have 3 O2 in here. There's no O2 in here that we need to worry on. So the only thing that we can worry is this 2 sub-reactions, okay? In this case, we really don't need to bother. This one is the only thing that we can bother, right? So we just multiplied once again by 2 to make it into 3. Because remember, if it's something like this, that's when you add it, not subtract, okay? The only reason where you're going to subtract or divide is when they're on the opposite sides, per Hess law, okay? That's how I do it. And see, so to do this, it's going to be 1 divided by, let me turn it to scientific. So 1 divided by 2.0 times 10 to the negative 35. So it's going to be 5 times 10 to the 34th. Okay. And then this one is going to be 1 divided by 4.0 times 10 to the negative 3. Then square it. It'll be 62,500 plus the other one. It'd be 3.6 times 10 to the negative 17. So after you do that, 500 plus 5, then to the 34th, you get 5. Yeah, that's recent. It's weird. It turns into like 5 times 10 to the 43. Okay, that's your answer. All right, so we're going to talk about, in this one, enthalpy. And before we discuss enthalpy, we're going to go back again and talk about these 2 processes. So the first process is exothermic process. So exothermic process is any process that gives off heat. So that's the key word, gives off heat. And the energy will be listed as a product. So that's also very important. If it's endothermic, it's in any process that heat is required by the system. So meaning it's either absorbed or it's necessary for the reaction to occur, and that the energy is listed as a reactant. And this is how it is in a potential energy diagram. As you can see, in the exothermic, we are releasing heat because we went from tons of heat, as indicated in this graph. Now it turned downwards, so we're releasing heat. And notice also that your activated complex, which is your activation energy, right here on the EA, we need to overcome that, right? And in this case, we don't need to overcome as much. So you're just overcoming, in fact, the erase everything, this part. It's really small. In your endothermic, what's happening is that you're kind of going uphill. So when you're going uphill, it takes a lot of energy, right, to go uphill. And instead of just overcoming from here to here, now you're actually going from your starting point into that peak of that mountain. So that's the way I think about it. Okay, so in the exothermic, your delta H, which is the enthalpy, it's going to be negative. If it's endothermic, your delta H is going to be positive. And just a reminder again, your activation energy on exothermic is really small. That's the reason why you're able to release the heat and have no problem with it. And it's going to be delta H. In here, you require a lot of energy to go from the start into the peak of the mountaintop just to overcome the activated complex and also your activated energy. So then you can create your product. And your delta H in here is positive. Okay. So enthalpy is used to measure the heat that is gained or lost by system that is at a constant pressure. So this is a form of extensive property, meaning it's something that is meaning that it depends on the amount of matter in the sample, right? So that's what extensive property means. So depends on the amount of matter in the sample. And again, so this is how you calculate it. If you have enthalpy in both products and reactants, the way you calculate its difference is you're subtracting your products minus your reactants. Oops. When delta H is positive, it gained heat, and when delta H is negative, it lost heat. Okay. That. Okay, so now we're going to talk about delta S. So delta S, which is also known as entropy, is the measurement of disorder of a system, and it's temperature dependent. So the way I think about it, it's the how energy is being dispersed on a something. So something in here would be your system. So just a reminder what a system is versus surrounding. So system, the way I think about it is if you are studying, it's a bad example. Let's say you're doing an experiment with a test tube on, right? So your system in here is what's inside in that test tube that you're measuring with. So this is your system. And your surrounding would be right here. The air, anything that is just outside of what's in that test tube. So that could be the air, that could be the temperature, that could be the humidity and such. So that's your surrounding. And entropy is actually the second law of thermodynamics. So some stuff you kind of not really need to know. And the only thing that you should know in here is that the entropy decreases as it becomes more organized. So entropy I think the way a chemistry teacher, like a general chemistry professor would say it, is how messy your room is. So the messier it is, the increase the entropy is. So you can kind of think about it in the same analogy as in here with the solid, liquid, gas. In solid, this is your molecule. They're all tightly packed. With liquid, they're kind of like this. They're not as tightly packed, but there's like vibrational in there. So they can like move around, unlike here, which there's little to no movement. And with gas, there's a bunch of different ones. So you have vibrational, rotational type of motion. So that's the reason why the entropy for gas is really big. So the entropy, remember, is greater with more molecules because you have a lot more stuff, and the greater its dispersal. With increased temperature, per gas law, what's happening is that basically those molecules, kind of like a ball, they're just going to like bounce back and forth within that system. And when the volume increases for gases, the same thing. Temperature and volume is directly proportional with one another with a gas law, right? If you increase the temperature of stuff, you're also increasing the volume of stuff. When delta S is positive, that means the entropy increases. When it's negative, the entropy decreases. Okay, and then the last one is going to be Gibbs Free Energy. So Gibbs Free Energy is the energy associated with a chemical reaction that can be used to work. So how is this delta H, which is your enthalpy, which we discussed, and our entropy, which is delta S, not, and the temperature is related. They can all be summed up in this formula right here. It's delta G equals delta H minus T delta S. Okay, as you notice, delta G and delta H is proportional with one another, and same thing with delta S, okay? So just a recap, if you're exothermic, which means the delta H is negative, that means it's favorable, okay? When delta H is positive, that means it's endothermic, they don't like that. When entropy is negative, that means there's a less disorder, so technically it's, that's weird. Technically they favor more disorder actually, and less disorder is not being favored. Okay, Le Chatelier principle. So Le Chatelier principle basically tells you what kind of changes are going to occur if you change its temperature, pressure, concentration, stuff like that. When you increase the concentration of a substance, you're going to shift it away from the substance. And the reason why is because it's like a teeter-totter. In a teeter-totter, when you put one stuff on one side, right, in order to balance it with another, you're going to put the stuff that you're shifting into the stuff that don't have enough weight, right, to make that teeter-totter level. So that's the reason why you're shifting it away from the substance. So that's the way I think about it. It's a balance game for me. And why? Because extra concentrations needs to be used up. Now, it's the same idea when decreased concentration of a substance, and the shift is towards the substance. Now, what's happening here is that you have a teeter-totter here. You have one stuff in here, and what's happening is like you're taking away this one stuff that you have to level off the plank, right? If you take it out, obviously it's not balanced anymore. You can't put it back here, because if you put it back here on away from the substance, in this case, which in this one, it's going to be on one side of the teeter-totter, it's going to be unbalanced again. and you need to put it back here just so it will balance it out, right, to be all good. Now the pressure is kind of a counterintuitive, not really counterintuitive, but it's kind of hard to understand. But just remember, when you increase the pressure of gas, you need to move it towards the fewer moles of gas, right? So for gas, pressure and volume. So with an increase of pressure, the volume decreases. That's just the one of the gas laws. And decreased pressure of system, it's going to go towards more moles of gas. So just remember, pressure decreases, volume increases. With an increased temperature, it's away from the heat or energy. So exothermic is being favored in here. So extra heat, energy must be used up. When there's a decreased temperature of the system, it moves towards the heat, energy, and exothermic reaction. More heat energy needs to be produced to make up for that loss. Now, this is the special one. As a catalyst, there's no shift. And the reason why there's no shift is because we're not really using up one of the substance in there. So the only purpose of catalyst in there is to speed up the reaction. It's not really doing anything with the concentration, with the pressure, and temperature. Solubility product. So solubility product, it's denoted as Ks. Most salt dissociate into ions when they dissolve. So, for example, you have this one, it turns into this one when it's dissolved, right? And can be expressed with just this. So just remember, in an equilibrium, you don't express solid and liquid. You only express aqueous and gas. And then this is solubility, and S2 minus turns into this. Just remember, this only applies to aqueous and gas. This don't apply to solid or liquid. That's every equilibrium problem. Okay, and that's about it.